Okay, let's move to the next chapter. So during this couple of slides, we basically discuss and explain the operation of clampers. So this is clampers. So previously we discussed the clippers, and during this session we found that so using this general purpose or this rectifier diode, we can basically clip the input signal at different levels. So depending on the uh, barrier voltage of the diode or the externals or DC sources, we add as the voltage bias voltages, so we can simply clip the input signal as we wish. Either we can clip the input signal from on the positive cycle, or we can clip it from the negative cycle, or we can do it on both the positive and negative cycles. So this time we may discuss the clampers. So this particular circuit basically have mainly have three elements. In general, we have these resistors. So then we have diode. So the third one, we have this capacitor. So here, this is the key element in this particular circuit. So without these capacitors, we cannot have this clamper. So the in this particular circuits, these clampers, so the significant contribution comes from these capacitors. So we'll see how these capacitors or the clamping circuits work. So before that, so we will try to understand the behavior of the capacitor circuit. So let's have a very simple circuit. We have a resistor and we have capacitor here, and we connect it to a kind of a DC source. So we have a fixed DC source of E volts, and we have resistor, and so we have current. So we have the capacitor. Okay. So before explain the behavior, we'll try to get a very simple equation. So just apply Kirchhoff voltage law for this particular circuit. So let's assume the current flow through the circuit is IT. For the time being, let's assume it's a kind of a time dependent. So then the voltage across the resistor, so ITR, and the voltage drop across the capacitor VCT, and those sum should be equals to E. So the source voltage is actually equals to the current time the resistor, which is the drop across the resistor, voltage drop across the resistor. So this is the voltage drop across the capacitor. Okay. So so we will basically and we can analyze this circuit, or we can solve this equation. So it's a part of the circuit analysis too. So for the time being, we can do like this. Yes. So for example, so we know that this current flow through the this IT is the current flow through the capacitor. So we know that for the capacitor, the induced current equals to the C times the derivative of the voltage. So this is valid for the capacitor. So this is for the capacitor. So by plugging it to here, so we know that this IT is the current flow through the capacitor, and the voltage drop across the capacitor is VCT. So we can simply replace this IT with C times the derivative of the voltage across the capacitor plus VCT equals E. So from this one we can obtain a differential equation. So this is the differential equation. This is first order differential equation. Differential equation. So by solving this first order differential equation, we can get expression for the voltage across the capacitor. Okay. Sorry, we have CR here. So we can get a kind of expressions by solving this first order differential equation to get for the voltage across the capacitor. So this is a part of the circuit analysis tool. Circuit analysis tool. So we'll keep it for the circuit analysis tool. So but we can build a logic to obtain this output. So how do we get this one? So at t equals 0, so what about the voltage drop across the capacitor? So there won't be any voltage across the capacitor, because so we just plug the capacitor in between the resistor and the source. So the initial voltage would be 0. So if so the voltage drop across the capacitor is now 0. So what about the current flow through the network? So the current flow through the network. So this is the voltage drop across these two plates is 0, means so at t equals 0, capacitor act as a short circuit element. At t equals 0, capacitor act as a short circuit element. So that's why this capacitor. So that conclusion we basically made on this. So the capacity at t equals 0, the voltage across the capacitor is 0. So based on that, we can claim that at t equals 0, capacitor can be replaced with a kind of a short circuit element, because the voltage drop across the two terminals is 0. So then the initial current IT at t equals 0 is equals to E divided by R, because no drop across this capacitor. So the VC0 is 0. So then the current flow through the network would be initially at t equals 0, E divided by R. So this is the current at t equals 0. So what happens when t goes to infinity? So infinity means, so we basically pick a value which is relatively large and treat it as in t goes to infinity. So t is infinite. So what happens now? Initially the capacitor got 0 voltage, and with this current, so this capacitor get charged. Up to which level capacitor can charge? So it can basically charge up to the voltage which is appear across its two terminals. If you apply 10 volt across the capacitor, after a certain time capacitor gets charged up to 10 volt. If you apply 20 volt across the capacitor, so after certain times capacitor gets charged up to 24. So likewise, once this t goes to infinity, so this capacitor basically charge up to VCT, charge up to E. So E is the maximum voltage which this the E is the maximum voltage appear across this capacitor. Okay. So but at that time what happens? If this capacitor charge up to E, so then there won't be any drop across this resistor. So because the source value is E and the capacitor also charge up to E. So then the net voltage across the resistor would be 0, and when t goes to infinity, your current should be 0. So there won't be any current flow through the network. This is also obtained from this equation. So for example, so if you apply a fixed DC source of E, we know that the current should be 0 because the derivative of the constant would be 0. So then this ideally after certain times, so this capacitor gets charged up to E, and the net voltage across the resistor would be 0, and then no current flow through this one. So if you draw these two together, so this is the variation of the capacitor. So T, so this is the voltage across the capacitor. Initially, it starts from 0 and it's gradually build the voltage across the capacitor up to E. So this is actually, so it's something like that. So this is E. So similarly, for current, so it's something like that. So initially the current flow through the network is E divided by R. After a certain time or t goes to infinity, the current flow through the circuit would be 0. So this becomes E divided by R. So this is the variation across the voltage across the capacitor, and at the same time this is the current flow through the capacitor. So this basically covers, this is called as the charging effect of the capacitor. So this is charging. So because once you supply of connect a DC source, so the voltage across the capacitor would be gradually increase up to its maximum. So then from 0 it's basically charged up to the value of the source. At the same time the current is simply converged to 0, and initially the current would be E divided by R. So once you consider a capacitor, so this is the nature of the capacitor. So this is the capacitor. So let's assume, so this is the charging effect and this is the discharging effect. So this is the charging process of the capacitor. So during this period, so the capacitor gets charged. So from here onwards, capacitor gets discharged. So this is the simple phenomenon happen inside the capacitance. Once you connect a source, it basically gets charged. Once you remove the source, it basically get discharged.